Bronsted Lowry acids are proton donors, Bronsted Lowry bases are proton acceptors. Well, to be a proton donor, essentially, you just have to have H in you. Okay, so any acid that you're going to come across will have an H in it. There are others, but none of your concern. To be a base, in order to accept a proton, most often you're going to have a negative charge. Okay, so any negatively charged ion, like Cn-, could act as a base. There are some exceptions. The ones that you're going to see most often would be water and then ammonia. Okay, ammonia is another base that does not have a negative charge but still accepts protons. So, if you're given a reaction, you can just see which entity, which reactant is the acid or the base, just by following your H's around. So here's my H here. It was donated to the H2O, and I can see that because my water has turned into hydronium. Okay, it has accepted a hydrogen. So if it accepted a hydrogen, it must be acting as a base. Water can also act as an acid, but not in this instance. And you see HCN has turned into CN, so it has lost a hydrogen. So therefore, it must be an acid. The two pairs involved, so you have HCN, Cn-, H2O, and H3O+, those are called conjugates. And you see up here, HCN, the acid turns into the conjugate base Cn- or cyanide. Whereas water, the base, turns into hydronium, the conjugate acid. Okay, each conjugate acid base pair differs by just one hydrogen. Okay, you need to know more than just the definition of a Bronsted Lowry acid and base. You're also going to have to predict a reaction in acid-base. Just like in redox, the first step was to determine your entities. Very similar to the rules involving redox. However, in redox, if you had an acidic solution, you would have H+. In acid-base theory, you'll never have H+. Okay? Sometimes you'll have hydronium ions, and only when it's a strong acid. So, as an example, you see here hydrochloric acid. In redox, you would have put H+ and Cl-. In acid-base theory, you're going to put hydronium and chloride. Okay, and the reason I'm going to break that up is because HCl is a strong acid. If you recall on your acid-base table in your data booklet, strong acids are the top 6. Anything above that will dissociate into hydronium and chloride. If it below, like hypochlorous acid, notice it does not break up. It's weak, so that means it does not ionize very much. So any weak acid will not break up. Okay, and then as before, you identify all your acids as being, identify your entities as being acids or bases, identify the strongest of each, then write your net reaction. So as an example, if we were to react hydrochloric acid with a solution of sodium bicarbonate. Well, let's first write out the compounds likely. So you have HCl aqueous and then sodium bicarbonate. Okay. Well, I have a strong acid. Okay, and so I remember that those will ionize and list the entities as such. It's aqueous, so there's water around. Sodium bicarbonate is a soluble ion of compound, so just like in redox, those dissociate. But I'm not going to dissociate the HCO3 because it's a polyatomic ion. Okay, and just like in redox, those always stay together, And to firm up that idea in acid-base, if I look on my table, this is an acid, but it's a weak acid. It's also a weak base, and weak acids and bases do not split up. Further, I'm going to now identify everything as acid or base, just using my table. That's acid and base. Sodium would be a spectator, and then bicarbonate is both. Be careful with these ones, okay? Notice it has an H in it, which most often means it can be an acid. There are some exceptions there. But also it has that negative charge. What's that mean? If you can be both acid and base, just like water, that means you're going to be amphiprotic. Or amphoteric is another term for that. So I want to carry on predicting this reaction. Identify the strongest of each. Well, anytime you have hydronium, it's always a strong acid. Bicarbonate is the lowest on the right-hand side, so it's your strong base. I'm going to have hydronium plus bicarbonate produces H2O, conjugate base of hydronium, and carbonic acid, the conjugate acid of bicarbonate. And to finish these off, you have to identify the position of equilibrium. Acid is above the base on your table, therefore greater than 50%.